offers a rich ground of experimentation and analysis in the field of cancer diagnosis. The structured features such as a unique patient IDs, diagnosis type, and the average values of visual cancer characteristics make it an excellent candidate for machine learning and data analysis projects. Here's how you might explore the dataset. For the objective, first understand the dataset. Gain the true understanding of the dataset structures and its features. Second, explore patterns and relationships, such as uncover patterns in the data to better understand the relationship between visual cancer characteristic and the diagnosis. Third, build predictive models. Create machine learning models to accurately classify cancer as either malignant or benign. The last one is generate hypotheses for further research. Use finding to generate hypotheses for medical or scientific research.
Good morning, everyone. So, my name is Rashika Afina. So today I will introduce to you guys the dataset descriptions of this cancer data. So first of all, the dataset composes detailed information about tumor characteristic with each observation identified by a unique ID. So we have like 6 unique ID, which means the first is ID, a unique integer identifier for each observation. Radius means the average radius of the tumor representing size. Texture means the average texture value indicating surface patterns. Perimeter means the mean perimeter of the tumor, which is an indicator of the shape. Area means the mean area, providing an estimate of the tumor size in terms of surface coverage. And lastly, we have smoothness mean, which means reflecting how uniform the tumor surface is. So one of the strengths of this dataset is its completeness. All columns have complete data with no missing value. So we have 2 data types, which is integer for the ID column, float for all the measurement columns, like radius mean, texture mean, and etc. For a closer look, we have a few sample entries. Observation 1 with an ID 842302, the tumor has a radius 17.99, a texture of 10.38, a perimeter of 122.80, an area of 1001.0, and a smoothness of 0.1184. So this dataset can be instrumental in identifying trends and patterns in tumor measurements. Researchers can use it to classify tumors, detect anomalies, or develop predictive models for cancer diagnosis. For instance, variations in smoothness or area might correlate with malignancy, offering critical insights for oncologists. So in conclusion, this dataset is more than just numbers. It's a powerful tool for advancing our understanding of cancer diagnosis. By leveraging this adjustment or measurement.
For methodology, we need to do the data acquisition and preparation, which the dataset used for this study was sourced from the uploaded file, cancer data. It contains key features of tumor measurements such as mean radius, texture, perimeter, area, and smoothness. The dataset was prepared to study the relationship and patterns among these features for potential classification and clustering. So first, we need to do the data loading to generate the coding. The cancer dataset was imported as a CSV file and prepared for analysis. Non-numerical columns were excluded and the numerical features were standardized to ensure comparability. And the dataset was then checked for missing values, which were addressed to maintain the data integrity. So next, we need to do the library installation and loading. Essential R package were installed and loaded, including ggplot2 for visualization, notice for normality testing such as psychological statistics, statistical functions, and advanced statistical methods. And then we need to do the data inspection. The initial rows of the dataset were examined using the head function to understand its structure and contents. The last selection of numeric variables. The initial rows of the dataset were examined using the head function to understand its structure and content. The second thing that need to be in the coding is a principal component analysis, which known as PCA. We need to compute the covariance matrix, where the covariance matrix of the numeric data was computed to understand the variance and covariance among variables. And the second is eigenvalue decomposition. Eigenvalues and eigenvectors of the covariance matrix were calculated to identify the principal components. And the script plot generation. A script plot was created using ggplot2 to visualize the eigenvalues and determine the number of significant principal components. And PCA execution. This PRCOM function was utilized to perform PCA with scaling, producing principal component scores for observation. That is normality assessment of principal components, which we will generate Shapiro test and QQ plots. We will see the result later on. And then the first principal components were tested for normality using the Shapiro test to assess the assumption of normality, which the Shapiro test is a statistical test used to check whether a dataset is normally distributed. It calculates a test statistic and a corresponding p-value. For QQ-plot, this will generate for visual inspection of the normality of the principal components, which QQ-plot is a graphical method to assess if data follows a normal distribution. It compares the quantiles of the dataset against the theoretical quantiles of a normal distribution. For outlier detection, we have 4, which Mahalanobis distance calculation. This is to compute and to identify multivariate outliers within the dataset, and threshold determination. The threshold based on the chi-square distribution with a 97.5% confidence level was established to flag potential outliers. For outlier identification, observation exceeding the Mahalanobis distance threshold were identified as outliers. And for visualization, a scatter plot of the first two principal components was created, highlighting the detected outlier. For the last one, we have factor analysis, which initial factor analysis. It is an exploratory factor analysis which conducted using the FF function from the package, specifying two factors and employing maximum likelihood estimation without rotation. And we have varimax rotation is to achieve a more interpretable factor structure. Varimax rotation was applied and the rotated factor loadings were examined. And the commonality assessment, commonalities were evaluated to determine the proportion of each variables, variance explained by the extracted factors. And the last one is factor loading visualization, which a factor diagram was generated to visually represent the factor loadings and their relation.
I am Noornaja and I will briefly explain the result. We obtained 3 graphs: square plot, QQ plot for each principal component, and scatter plot for outliers. This square plot shows that PC1 has the highest value of the eigenvalue, and the point drastically dropped after PC1, and this is called elbow point. Next, we have QQ plot. This plot is to show if the distribution of each principal component follows normal distribution or not. For PC1, most of the points aligned with the diagonal indicates that it follows a normal distribution. For PC2, there are some points that align with the diagonal and some are not. Lastly, for PC3, most of the points align with the diagonal point and only a few that are not aligned. This scatter plot is to show outliers from principal component. As we can see, most of the points are in black, meaning that they are primary data. The red points is the outliers of the data. These represent unusual and inconsistent cases or significant deviation.
So lastly, for the conclusion, I will conclude all the relationships between all variables from the dataset. So firstly, which is age and cancer stage, which is older age groups show a high correlation with advanced cancer stages, indicating delayed diagnosis or aggressive disease progression. Next, which is tumor size and lymph node involvement, which is larger tumor sizes are strongly associated and positive lymph node involvement, suggesting a link between tumor growth and metastatic potential. Next, genetic markers and cancer types, which is specific biomarkers are more prevalent in certain cancer types, which aiding targeted therapy decisions. So therefore, by using multivariate regression or classification techniques, predictors like tumor size, age, and genetic markers collectively achieve high accuracy in predicting cancer stage or survival probability. So, principal component analysis, which is PCA, reveals that a few key variables explain the majority of variance in patient outcomes. Next, which is I am going to go through the implications for the healthcare industry. So firstly, which is dimensionality reduction, which since PC1 captures most of the variance, it can be used to represent the dataset effectively with minimal loss of information. Secondly, focus on key drivers, which the strong explanatory power of PC1 suggests that a single or a few dominant factors drive most of the variance, which can guide targeted interventions or streamline decision-making processes. Next, which is treatment optimization, which multivariate analysis enable the identification of patients most likely to benefit from specific treatments based on tumor and demographic profiles. Next, data normality with QQ plots showing approximate normality for PCs. Parametric statistical models can be employed effectively.